Alright, so welcome back to your favorite inorganic tutor YouTube channel once again. Today is another episode and we want to look at how we can do today is full computations. We want to look at how we can find the eigenvalues and the eigenvectors of this matrix A. But before I begin, let me give a very big shout out to everyone watching me out there. Merry Christmas in advance. Please enjoy the Christmas, and we are trusting God for the best in the coming year, in the preceding year as well. So we want to know how to do computations on finding the eigenvalues and the eigenvectors of this 3 by 3 matrix. Of course, we know that we have to set up the characteristic equation, and that is the determinant of the matrix given minus lambda I, right? The determinant of the matrix given minus lambda I, and that should be equal to 0. And this is the characteristic equation. So what we have to do is that we have to find I, and that I, which is the identity matrix, should have the same size as the matrix given, right? So the real idea is that actually there was no I, but don't forget that you cannot subtract a scalar from a matrix. So that is when they introduce the lambda, the I to the lambda to make sure that we have lambda multiplying an identity matrix. And don't forget that when you subtract or you add identity matrix to any matrix, it doesn't change the shape of the matrix. So that is why we introduce the identity matrix to make the work so easy, right? So the identity matrix of this size, which is a 3 by 3 matrix, should be equal to 1 0 0 0 1 0 0 0 1, right? So we multiply this by lambda, right? So lambda I of this matrix right here is going to be lambda 0 0 0 lambda 0 0 0 lambda, right? So this we have right here. We're going to subtract this from the matrix given. Then we find the determinant of that. Then we equate it to 0 to find the eigenvalues. Then we can proceed to find the eigenvectors. So right here, we know that our A, which is the matrix given, minus lambda I is equal to 4 1 2 1 4 1 2 1 4 minus lambda 0 0 0 lambda 0 0 0 lambda, right? So this right here, when we subtract this, we already know that we are going to have A minus lambda I will be equal to 4 minus lambda. Then we have 1 2, right? Then we have 1 right here. Then we have 4 minus lambda. Then we have 1 right here. Also 2 right here. 1 right here. And then we have 4 minus lambda, right? So this right here, we find the determinant of this matrix right here. Then we equate it to 0. Then find the eigenvalues of that particular equation. So this right here we find the determinant of this. Four minus lambda right? So we are finding the determinant of this matrix right here. So we already know that when you find the determinant using the first row operation, so this is the first row operation that we are going to use, right? So 4 minus lambda, then the 2 by 2 matrix form under this is going to be 4 minus lambda, 1, 1, 4 minus lambda, then minus 1, 1, 2, 1 minus, then we have plus 2, 1, 2, 4 minus lambda, and also 1. Right here. So this right here, we find the determinant and then we equate it to 0. So this right here, we're going to have 4 minus lambda multiplied by 4 minus 4, 4 minus lambda, 4 minus lambda, minus 1 into 4 minus lambda minus 2, right? Plus 2, 1 minus 2 into 4 minus lambda, right? So we expand this, we expand this, we expand that. After that, we simplify and equate it to 0. So 4 minus lambda into 16 minus 4 lambda minus 4 lambda plus lambda squared, right? Minus 1. Minus 1 into 2 minus lambda plus 2 into 1 minus 8 plus 2 lambda, right here. So this right here, we're going to have this right here is going to be 16 minus 8 lambda plus lambda squared minus 1 minus 2 plus lambda plus 2 minus 16 plus 4 lambda, right? So we expand this right here and we know that this can take off this. So we have 4 minus lambda into this will give us 15 lambda squared minus 2 plus lambda. This right here will give us minus 14 plus 4 lambda, right? So when we expand this, we are going to have 4 times 15, right? And that is 60, right? And then 4 times minus 8, that is minus 32 lambda plus 4 lambda squared minus 15 lambda plus 8 lambda squared minus lambda cube, right? Then minus 2 minus 14 is going to give us minus 16. And also lambda plus 4 lambda is going to give us 5 lambda, and that should be equal to 0, right? So we proceed from here. So 60 minus 16, and then minus 32 lambda minus 15 lambda plus 5 lambda, and then plus 4 lambda squared plus 8 lambda squared minus lambda cube, and that should be equal to 0, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So now let's simplify this. What we can do subtraction right here. So we know that this right here is going to give us 44, and then minus 32. This right here will give us minus 10. So it's going to minus 10 minus 32 is going to give us minus 42 lambda, right? And then this right here is going to give us plus 12 lambda squared minus lambda cube, and that should be equal to 0, right? So this right here, we can rewrite this as minus lambda cube plus 12 lambda squared minus 42 lambda plus 44, and that should be equal to 0, right? This, we can see that we have a polynomial equation. Because we were having a 3 by 3 matrix, we have to form a 3 systems of variables, or, right, we have to have cubic equation, right? So this right here, we know that we can do what we call try and error, so that we can find the first value of lambda and then use it to divide this polynomial and get the next two values, right? So we can use 2 right here. When you put 2 right here, we're going to get 0. So we have lambda minus 2, right? And then we can see that when we factor lambda minus 2 out, we can have lambda squared, all right? Lambda squared minus we can use what we call the long division. So lambda minus 2, then we put everything inside. So we're going to have minus lambda cube plus 12 lambda squared minus 42 lambda plus 44 right here. So we use this to divide this, and then we have minus lambda squared. Then we use it to multiply everything right here. So when you do that, you are going to have minus lambda cube, Then this right here is going to be plus 2 lambda squared, right? So we subtract, right? So we subtract, we're going to have here to be 0. Then 12 minus 2 is going to give us 10 lambda squared. Then you produce the next elements right here. So this right here, when you divide, you're going to have plus 10 lambda. Then we multiply with this, right? So we have 10 lambda squared, then minus 20 lambda, right? So we go down again, subtract. When you subtract, you're going to have this part to be 0, then minus 42 minus minus 20. So minus 42 minus minus 20, and that is going to give us minus 42 plus 20, and that is minus 22, right? So we have minus 22 lambda plus 44. So we go again. So it gives us 0, right? So this divide this, we have minus 22 right here. So this multiplies this, and we have minus 22 lambda plus 44 times 2, 22 times 2, and that is going to give us 44 right here, right? So we have this, consider this is 0, this right here is 0 as well. So this is the quadratic equation that we obtain together with this test of error. So we can see that this lambda minus 2 and then minus lambda squared plus 10 lambda minus 22 should be equal to 0. So this right here, we can now easily evaluate to find our values of lambda 1, lambda 2, and lambda 3. So this right here, we can say that we have lambda 1, lambda minus 2 should be equal to 0, right? So we have lambda 1 equals 2, right? And then we consider the quadratic aspect as well. So when we do this, we can easily evaluate this now. So let's try to avoid the negative right here. So can we have lambda squared minus 10 lambda plus 22, and that should be 0. So this right here, we have to use what we called the quadratic equation because we cannot easily evaluate this, right? So we have to use the quadratic formula, which says that lambda should be equal to minus b plus or minus square root of b squared minus 4ac all over 2a, right? And this right here, we can see that our a is equal to 1, our b is equal to minus 10, our c is 22 as well. So we can easily do that right here. So we have lambda is equal to, our b is minus 10, is going to be 10 plus or minus square root of 10 squared, is which is 100 minus 4 into our a 1 and our b, our c2 is 22 all over 2 times 1, and that is 2 as well. So this right here, we're going to have lambda equals 10 plus or minus square root of 100 minus 22 times 22 times 4, right? So that is 22 times 4, and that is 88, right? So we have this and this, we have 88 all over 2, right? So we can say that lambda is equal to 10 plus or minus square root of 100 minus 100 minus 88, right? And that is basically 12 right here all over 2, right? So when we do that, we can say that we have our lambda so when we do that, we can have our lambda 2 is equal to our lambda 2 will be equal to 5 plus 10 plus or minus square root of 2 over 2. We know that square root of 12 is 4 times 3, right? So we have 4, which is a perfect square. So we're going to have 2 outside, right? So we have 10 plus or minus square root of 4 times 3. And that is going to give us 5 plus square root of 3. We have the positive side to be 5 plus square root of 3. And then the next one is going to be 5 minus square root of 3. So this is our lambda 2 and our lambda 3. That is the eigenvalues for this question is going to be lambda 1 equals 2 and lambda 2 is equal to 5 plus square root of 3, and that of lambda 3 is 5 minus square root of 3. So now we can substitute this lambdas, which is the eigenvalue, to the evaluated matrix, then find the eigenvalues, the eigenvectors corresponding to this particular eigenvalues, right? So we already know, let me clean this part. So we have our lambda 1, which is equal to 2, right? So now we come here. So we substitute lambda 1, lambda 2, lambda 3 into the evaluated matrix where we had A minus lambda I. We evaluate it over there to find the corresponding eigenvectors to these eigenvalues, right? So we all know that this right here, A minus lambda I, is equal to 4 minus lambda, which is the matrix 1 minus 2, and then the next one is 1 and then 4 minus lambda, and also 1 right here, and then we have 2, 1, 4 minus lambda, right? So this is what we have to substitute the eigenvalues, which is the lambda 1, lambda 2, lambda 3, into this to find their corresponding eigenvectors. So right here, when you substitute for lambda 1 equals 2, when we do that, we are going to substitute this lambda 1 into this to form our first or to find our first eigenvector corresponding to eigenvalue 2. So this right here is going to be 4 minus 2, and that is 2, 1 right here, 2, 1, 2, 1, 2, 1, and 2, right? And we all know that to find the eigenvectors, we multiply it by the variables. Of course, you can use S1, S2, S3, but because we are talking about eigenvectors, I decided to use V1, V2, V3, right? So this right here should be equal to 0. But then, because we are talking about eigenvectors, of course, it's a matrix, so we represent this by 0, vector, right? So this right here. So now we are interested in finding v1, v2, v3, right? So in doing this, you can either use the Gauss-Jordan, right? You can use the Gaussian elimination or go by normal systems of equation, how you solve it, then you get your values right here. So this right here, let's use our normal way of solving systems of equation right here. So this right here is going to be 2v1 plus this and this, v2, this and this, 2v3, and that should be equal to 0. This is our equation 1. This right here to this, so we have v1 plus this and this, 2v2 plus this and this, we have v3, and that should be equal to 0. Equation 2. This and this, we have 2v1 plus this and this, we have v2 plus this and this, we have 2v3. That should be equal to 0. Equation 3, right? So we can see clearly from here, right here, is that this, or let me go right here, this equation 1 and this equation 3 are identical. They are same. They are the same. You can see 2v1, v2, 2v3, 2v1, v2, v3. So this equation 1, equation 1 and equation 3, they are identical. So we avoid the equation 3 and we work with either equation 1 and 2 or either equation 2 and 3. So now let's consider equation 1 and 2 and work with. So we cancel out equation 3 because equation 1 and equation 3, they are identical. So when we consider equation 1 and equation 2, what we do is that let's make v1 the subject in equation 2, right? So when we do that, we are going to have v1 equals negative v2 minus v3, right? And that should be equation 4, right? When you make v1 the subject here, it means we are sending any other variable to the right hand side, and that is going to give us negative 2v2 minus v3. So let's put 3 into equation 1, that is 4 into equation 1 right here. So when we do that, wherever we see v1, we put minus 2v2 minus v3. So we have 2 into minus 2v2 minus v3 plus v2 plus 2v3, and that should be equal to 0, right? That is equal to 0. So we're going to solve this right here. So when we expand this, you're going to have minus 4 v2 minus 2v3 plus v2 plus 2v3, and that should be equal to 0. And right here we can see that we have minus 2v3 and plus 2v3. So this takes care of this, right? And then we are going to have minus 4v2 plus v2, and that should be equal to 0. You can see clearly that this is going to be minus 3v2 equals 0. And this implies that our v2 is equal to 0, right? So far as we have been able to obtain v2, then we can equally obtain v1 and v3 from equation 4. So right here, when we put v2 to be 0 in equation 4, then we are going to have v1 equals negative 2 into 0 minus v3, right? So we have v1 is equal to minus v3, right? So nice, right? So we have v1 is equal to negative v3, right? So right here, we assume that if v1 is equal to positive 1, right? Or if v1 is equal to negative 1, then it means that v3 is going to be positive 1. So right here, this implies that v1 is equal to 1, which is always common value that we always choose. You can decide to pick any scalar, any number at all, but v1 is a most commonly number that we mostly use. Actually, it's not compulsory that you pick 1 to be v1. Well, you can pick any number, but make sure that it makes sense, because you are working with you are working as a mathematician. Don't go and pick any number from anywhere, right? So this right here, we can say that if v1 is equal to positive 1, then we can say that our v3 is equal to if v1 is equal to negative 1, then our v3 is equal to positive 1, right? Because v1 is equal to negative v3. So if v3 is positive 1, then v1 will be equal to negative negative 1. So we can say that, let me write it up here. The eigenvector corresponding to eigenvalue 2 is negative 1, 0, and positive 1. So this is the eigenvector corresponding to eigenvalue, which is 2. So I'll give the rest of the task to you. I find the eigenvector corresponding to eigenvalue 5 plus lambda, 5 plus square root of 3, and then eigenvalue 5 minus square root of 3. Find the corresponding eigenvalues, eigenvectors corresponding to these two eigenvalues. I'll leave, or should I provide the solution? No, I'll provide the solution at the comment or the description button. Please solve it. Don't forget to solve it. The moment you forget, stop learning, means you are dying. Go and solve.